would like to say a few words about my experience with Grégoire. So I first met him when I was doing my master thesis with Catherine Nicolis, and I, of course, followed his course on nonlinear science at the ULB. And I really enjoyed the course. And I also saw all the potential of these different techniques in the context of atmospheric and climate dynamics. Then I met him from time to time while doing my PhD thesis with Catherine Nicolis, and also after that, when he was picking up Catherine at the Royal Meteorological Institute of Belgium. And we had quite a lot of discussions. And as you know, he was very much interested by the application of nonlinear techniques to atmospheric dynamics and atmospheric sciences. So in general, so he provided me a lot of advices in this context, and I'm of course really grateful to him for all his advices. And during the weekend, I was looking to a few pictures and I found nice pictures, so I will share my screen with you now. And I will start slideshow here. Yeah, do you see the pictures? Maybe I should change the setting that way. Do you see? So it was a meeting organized in honor of Catherine Nicolis at the Royal Meteorological Institute of Belgium. And in fact, this was a very, very successful meeting, and Grégoire provided me a lot of help in this context and pointed out to several very key persons in the field of the application of nonlinear techniques in the context of atmospheric dynamics and climate dynamics. And I would like just to point out to, well, when I was looking at all these pictures, I realized that one of the presentation here by Michael Gill was on random dynamical systems and non-autonomous dynamical systems. And so the work I will present you today is precisely rooted there in this presentation. So I didn't realize that, but afterwards it was clear to me. So the work I would like to present you today is a work we have recently done, as I said, with Michael Gill and with Jonathan de Meyer. And the idea is really to try to understand the impact of the El Nino southern oscillation in the tropical Pacific on the extratropical regions. So just to present you the problem. So the El Nino southern oscillation is a coupled dynamics between the ocean and the atmosphere in the tropical Pacific. So just you have a sketch of this type of dynamic. Here you have the tropical Pacific basin with positive temperature anomaly here on the west part of the basin, and above this you have the so-called Walker circulation. And this is the normal condition, but at some point when the Walker circulation is weakening, you have displacement of this positive anomaly toward the east coast. So, and in this case, you have the so-called El Nino condition. And of course, at some point when it's weakening, you have again a displacement toward more normal condition, and even you can go to the so-called La Nina conditions, where you have a strong anomaly on in the western part of the basin. And associated to that, of course, you have the Walker circulation, which is playing a key role in these dynamics, but you can also measure that in terms of time series. So here, this is the Southern Oscillation Index, so the evolution of the difference of pressure between two specific stations in this region, so between Tahiti and Darwin. And you can clearly see that there is a low frequency variability developing in this region with typical timescales of a few years. Okay? So, and what is also clear is that there are some kind of teleconnections with other regions of the globe. So teleconnections are just covariability with other regions of the globe. So when you have, for example, El Nino situation, then you can have, for example, warm anomalies of the climatology over this region here, over Alaska and Canada here. That's just an example. And in fact, there are many, many studies that have investigated these teleconnection patterns, so these covariability patterns. And also, there were some mechanisms that were proposed to explain these dynamics. And this is the so-called atmospheric bridge. So, and it was proposed quite some time ago. So the idea is that you have some influence from the tropical Pacific toward the extratropics via the atmosphere. So, and we can of course wonder what do we gain when in the extratropics? What do we gain from this low frequency variability acting in the tropical regions? And of course, we are also interested to make even longer forecasts and trying to make a forecast based on this type of teleconnections. So there were a lot of works done in this context, but usually it's limited to let's say comprehensive models, and trying to understand that in comprehensive models is not easy. So, and the number of experiments you can do is quite limited. So what we decided to do here in this context is to analyze the so-called pullback attractors and their properties. So I'll come back to that in a minute. For a reduced order coupled ocean atmosphere model for the extratropics, and forced by let's say, a model describing dynamics in the tropical region. So you have here our extratropical model, which is coupled ocean atmosphere system, an idealized one. So you have a kind of closed ocean basin that would represent, for instance, the Atlantic, the North Atlantic or the North Pacific. And you have, on top of that, you have the atmosphere, which is two layers of atmosphere, and you have interactions between these two components, of course. And this is idealized, so this is a rectangular domain where we plug our dynamical equations. And what we did is, as a la Lorentz, so we build a reduced order model, and this reduced order model is a 36 variable model. And what we did is that we force one mode within the atmosphere based on the solutions that are generated by the tropical model. And we used, in fact, two different types of solution. One, which is a periodic solution with a typical period of 12 years. And so typical time between two very strong El Nino, in fact. And also a chaotic one where the typical time scales is of the order of 30 years, so it's much longer, but it was just to analyze so it's not very realistic, but we wanted to analyze what is the impact of stochastic of chaotic forcing. Okay, so we have our setup, and what we decided to do is to use some techniques developed in the context of the non-autonomous dynamical system. So you have your non-autonomous system here, where you have an explicit dependence in time here associated with the tropical forcing. And what we tried to build is this pullback attractor. So the pullback attractor, probably you know what it is. So here you have, this is just a simple sketch of that. So you have your phase space, you have your time here. And of course, the pullback attractor is a collection of invariant sets in time. So you have, this is the blue, blue structure here. And of course, this is just valid for one external forcing. So how can we build that? How can we get this information on this pullback attractor? Is by starting trajectories far in the past, let's say a set of 1,000 different trajectories starting from different initial conditions in the past, and look at their evolution, and we can try to build this structure, in fact. And just again, a picture of Michael Gill presenting that during this workshop in 2010. So yeah, this is the first result I would like to show. This is in the case of the periodic forcing case, and I present here the first Lyapunov exponent as a function of J. The small j here is the strength of the forcing imposed to our extratropical model. Okay, And just look at the blue curve here. So, and you have a zoom of this blue curve there. You have a zoom of this blue, oh, sorry, I come back. The zoom of this blue curve there. And you can see that, so if you start with j equal to 0, then of course you have the autonomous case, and the Lyapunov exponent is of this order, is of the order of 0.1, d minus 1. And if you increase or decrease j, you have a slight change. So you have an improvement of predictability. I don't see my my arrow. I should try to find it back. Sorry. Where is it? Cannot find my mouse. Anyway, so when you have this decrease, when you increase j, but then you have a jump toward another value, which is much larger, and you can have also a concomitant pullback attractor, so with different value of the dominant Lyapunov exponent. Okay, and so this is a very interesting result. And in order to get that, we started, in fact, from 10 different initial conditions in the far past, and we did that for every value of j we explored. And so you have concomitant pullback attractors for the same values of the forcing strength. And this is here trajectories that are generated by these two pullback attractors. On the top left, you have the evolution of the periodic solution, the forcing, okay, from for the extratropical model. On panel C, so the bottom panel on the left, you have the evolution of variable psi02, which is a variable within the ocean. And in fact, this is a very important variable within the ocean. This is, it describes a double gyre dynamics within the ocean. And you can see that for these two pullback attractors, you have very different low frequency variability, one which is very small and one which is very large in this case, so a much stronger double gyre dynamics within the ocean. And on panel B, so on the top right, you have the evolution of one variable within the atmosphere. And this, in this case, for pullback attractor 2, you have a variability, a low frequency variability, which is much more intense than for the other pullback attractor. And also in panel D, this is just the convergence of the Lyapunov exponent. So we have really distinct pullback attractors in this case. For the chaotic forcing case, you have a very similar picture, in fact. So, but in this case, you have a zone between 0.02 and 0.04 in the value of j. So you can see that on the left panel. You have, it's quite messy, in fact. And you can have, in fact, in this zone, you can have transitions between the different pullback attractors, basins of attractions, okay? And this is what you can see on the right side. You have the evolution of the variables. So you have the, on panel A, you have the enso-chaotic forcing, B, one variable within the atmosphere, and C, you have the evolution of this important variable within the ocean. And you can see that there are transitions between these different zones. You have transitions on millennial timescales. So, and yeah, so let me now come to the conclusions. In fact, what we have seen in this case, so we have studied this, let's see, the forcing imposed by the tropical regions on the extratropical region, for the periodic and the chaotic forcing case, and we have found several pullback attractors in the extratropics. I didn't discuss that, but they have also distinct stability properties. And what is really important is that we can have multiple pullback attractors that are present at the same time. And this, of course, has considerable implications for internal, let's say, climate predictions or projections, because what we are doing in climate science, so we start from a model, we start from several initial conditions, let's say 100, and we run these models. But of course, people are trying to extract some, let's say, low frequency variability signal within these runs, and what they are doing, they take an average of the ensemble. But in this case, if you have multiple pullback attractor, of course you have problems in doing that, because it will not provide you the right signal. So yeah, so we have to consider each ensemble member separately as a unique possible outcome and compute probability densities, of course. So thank you very much for your attention, and I just want to finish this with these very nice pictures of Grégoire and Catherine at this workshop in 2010. And of course, if you have questions, I'm
Thank you.
Happy to answer.
So there is time for questions.
I have a question for Stephane.
Yes.
Sure.
What is the difference between the Jean-Timmerman model and the Jean-Wallin model? Is this a coupling between shallow water equations and energy balance? If this is so, what I guess it is so, do you have also uniqueness of time-dependent solutions in an unbounded channel or not? Another question that I want to ask is, in all these problems for ENSO, the difficulty is the forcing needed to arrive at the desired result. The people usually, they don't say anything about the forcing, but what is happening is that the forcing needed is excessively large and unphysical. Is this the case here too?
So that's a very good question. So I'm not a specialist of the tropical Pacific dynamics, of course, as you know that much better than me. So this is a 3-variable system, which is so a 2-box model, okay? And you have the evolution of the temperature in the 2-box model, also with an equation for the description of the thermocline dynamics. So this is, I don't know if it's related to the second model you mentioned, this one, but for us, it was just a tool to force the other model. And of course, there were, as you said, several types of different models that were proposed in the literature, and sometimes, yeah, it could be very unrealistic dynamics. But here we try to get time series or trajectories that have some common properties, I would say, with the dynamics of the of ENSO in the tropical region. Of course, we know that's not a realistic description, but it was for our purpose. It was, I think, enough to figure out what is happening in the extratropical region. So thank you very much for this very tough question for me.
So are there other questions? There was one hand by Marco Salazar. Is no longer here, is he? So I have a general
okay.
Yes.
Sorry, I wanted to ask a question, but he already answered the question.
Okay.
Answer. Thank you very much.
Fine.
Thank you.
I have a general question. What are the observational data with which we can make comparison?
That's an even harder question. So one of the points is that I've got this question at another time. So what should be the strength of the forcing in order to get so let's say the observational strength of this forcing in order to figure out if what we did is reasonable, and in which range we should find our real dynamics. But clearly, that's difficult to answer. At least at this stage, I don't know how to answer that question and how to approach that problem in order to really have an idea about the value of the strength of the forcing we should add into the system in order to get our appropriate, let's say, dynamics in the extratropics. That's also a very good question.
But is it possible to compare on shorter time scales with what has been recorded?
I think it's even, well, we have only one trajectory, as you know. With the observations, we have just only one trajectory. So it's difficult to say something just based on one trajectory. We cannot build a kind of pullback attractor as we can do that in the context of these models. So at this stage, I cannot answer the question, but I think this is a very, very important question indeed.
Okay. Are there further questions? So if not, let's thank Stephane. And so we meet this afternoon at 1:30.
I would just like to add that we seem to have sorted the Meet Anyway system. So now it should work for those who try to get in, those who have already logged in. So something has been sorted. So hopefully you can join it more easily now. Even so, lunch break is a